In the last video, we started exploring Faraday's law in the context of a magnetic field which was spatially uniform but changed over time. Let's keep going with Faraday's law and investigate the case where the field is both not spatially uniform and potentially also varying in time. So we're going to imagine the case of a wire which is carrying current in the j hat direction, and a distance away from it, we've placed a square loop with side lengths s. And so before anything else, we'll want to focus on computing phi b. Remember, that is integral b dot dA. Using right-hand rule, we know that the wire will produce a field going into the page at the location of the loop. So our dot product is technically magnitude of b, magnitude of dA times cosine 180, but in absolute value, cosine 180 -1 we'll just treat as 1. And so we get integral b dA. And this time, unfortunately, b does seem to be a function of radius or distance from the wire. Recall from Ampere's law that b of a current carrying wire is equal to mu naught I over 2 pi r. And so let's go ahead and put that into our integral. We can obviously pull out mu naught I over 2 pi as constants, and we're left with integral of 1 over r dA. And so, of course, for those of you familiar with double integration, we can obviously do this as a double integral. But the approach we're going to take here is we want to do a single integral. Let's think about how we can slice up our area into regions which have a constant value of r. And of course, the way to slice that is to slice vertically. I can do a thin vertical strip with thickness dx. And then that strip is a fixed distance r away from our wire. What is the area of that strip? Well, it's our width dx times our height, which is s dx. So dA is s dx, and we're nearly there. So we can pull out s as a constant, giving us mu naught I s over 2 pi, integral 1 over r dx. Note that x represents the position along the x-axis, r represents the distance from the wire. If I simply state that x equals 0 is located at the position of the wire, then we can state that r is equal to x. And so we're left with mu naught I s over 2 pi integral dx over x. And we can now easily find our bounds of integration. We're starting at this end of our loop and going up to this end. And so our bounds of integration will be from x equals a to x equals s plus a. And with that, let's write our final answer. So we got mu naught I s over 2 pi, natural log of x evaluated from a to s plus a, which I'll choose to simplify using my properties of logs as mu naught I s over 2 pi, natural log s plus a over a. And so from here, let's apply Faraday's law. And we're going to imagine two scenarios. Scenario 1, let's imagine that I itself is a function of time. In that case, we can say that d phi b by dt, and I'm writing this in the abstract case, we can talk about specific functions of time, is equal to, note that all of the parameters of the problem are constant, s isn't changing, distance from the wire isn't changing, mu naught and 2 pi are obviously constants, so we'll pull out mu naught s over 2 pi, ln s plus a over a, times I prime of t. And at this point, depending on what the exact value of I of t is, we can just compute its derivative. So for example, if I of t were equal to some constants times time, right, we would replace I prime of t with just c. So that is going to then be the magnitude of our EMF. So let's now consider the direction in which our EMF acts. So we originally had a current which was going up and a squared loop to the right of it with side length s. And so let's consider two cases. Suppose that I prime of t is greater than 0, case A, and case B, I prime of t is less than 0. Of course, if I prime of t is equal to 0, then we have no induced EMF. And so again, let's recall that since our current was going up, the field at the right side of our wire is going into the page and coming out of the page here, but that is of no concern. And so if I prime of t is greater than 0, that means we're producing more flux going into the page. So phi b increases into page, or in the negative k hat direction. That tells us that our EMF is in the positive k direction, so as to oppose those changes. And so what does that mean? That means our EMF is induced counterclockwise. In other words, if there's an actual square wire that is a conductor, our current will begin flowing counterclockwise. By contrast, if I prime of t is less than 0, phi b decreases in the negative k direction. And so that means that our EMF would be in the negative k direction and drive current in a clockwise manner. So let's now consider a completely separate scenario. Again, we'll pull our result from earlier, which was that phi b is equal to mu naught is over 2 pi ln s plus a over a. And this time we'll consider I to be constant, but we'll give our loop motion to the right. So imagine that our square loop is moving to the right with speed v. As we're moving to the right, hopefully it's clear to you that we're moving into a region of weaker magnetic field, and therefore our magnetic flux should probably be decreasing. Let's see how that shows up in the derivative. So let's compute d phi b by dt. And in this case, what is the variable which is changing? Well, the variable which is changing is simply a. To simplify our differentiation, I'm just going to quickly use properties of logs to rewrite our phi b. So we'll have mu naught is over 2 pi, and then we'll just write it as ln s plus a minus ln a, just to avoid needless product or quotient rule. And so therefore, d phi b by dt, the mu naught is over 2 pi, those are just constants. And taking our derivatives, we get 1 over s plus a minus 1 over a, and don't forget your chain rule, times dA by dt. So note, I've applied the chain rule term by term, but they both contribute a dA by dt. And lastly, what we realize is that dA by dt, the rate at which our distance from our wire is changing, is simply v. So we're left with mu naught is over 2 pi times 1 over s plus a minus 1 over a v. And so lastly, let's quickly consider, in this case, what our direction of induced EMF would be. Again, we've got a field which is going into the page. We are moving to the right, so away from our wire, which means that naturally our magnetic flux into the page is decreasing, which will induce an EMF, which goes clockwise.